Okay, so so in the previous lecture we have talked about and linear regressions. But as you can see from the implementation, the data actually shows like a lot of like nonlinear structures. I mean, in fact, that will be a quadratic so equations. So the situation is, if the data is actually nonlinear, how can we use those like nonlinear and the relationship? Um, I mean, and to do these kind of like regression problems. So in general, so this is the, I mean, the theme of today's lecture is nonlinear relationship. Right. So for example, in this cases that we have is x is actually in R and which is 1D. So what we can do is we can apply some nonlinear transformation to those input features and replace x by some nonlinear function. So what we can do is we can apply nonlinear transformation phi. So that means it actually map into phi x right here. So, and then let's say this phi x is in R big D, right? So then we and what we think about this is our model this becomes y equal to phi x times w plus epsilon right here. So as far as this phi is fixed, this whole thing is still linear with the parameter. It's a linear. With w, which is the parameter. So that is good. And also we can think about this probabilistic model that is y given x and the theta right here is actually a normal distribution where the y given the phi x times w with the standard deviation of sigma squared. Okay, so this is basically, it's kind of the extension of this linear and the linear regression in the situations. But the question is what kind of phi that we can and actually apply. One very commonly used choice is actually polynomial expansion of degree of D. So, and the popular choice is we actually trying to using this polynomial expansions of degree of D. So this phi x is equal to, so you can think about x to the 0th, x to the 1th, to x to the d. So, and of course, this x to the 0 is precisely equal to 1. So in this case, this will be r little d plus 1. Right, so this is actually the polynomials up to the degree of the little d. But the issue is, and of course, if d is precisely equal to 1, this is go back to our previous like linear regressions. But if we choose like larger d that we have, it's getting and more complicated in the situations of the polynomials. Right, so this I'm actually give you a degree of freedoms that you can choose that actually parameters of dimension d. So the question is how to choose the parameter. D. So the small d, so that is underfitting. So that means it's basically this training error will be high. If we have a new data, we have prediction error, so sorry, and a validation error, and like test error will also be high. So this basically says my predicted value in the, for the new data is deviate from truth a lot. Then next is, situation is with the large D. That is, if the D is large, that means the whole degree of freedom is pretty high, and it's the situation of overfittings. So, so what is that? For the overfitting is the training error is low, but testing error is high. You will see that momentarily. Okay, so i.e., this cannot generalize to new data. So generalize to. So like this whole, and the situation cannot generalize to new data. So that's also really bad. So from this, we know we can't choose a very small d. In the meantime, we can't choose a very large d as well. So there's like some sweet spot that we can choose for the optimal b and choice of these. Okay, so how to actually choose this d's, and we're going to talk about the strategy is using cross validations. Okay, so cross validation obviously is very, very crucial and very, very important. But we will talk about in a moment and momentarily once we finish the next concept. Right here, we assume this x is actually just 1D. If my x is high dimensional, which is a vector, it's in RP, so we can generate a bunch of other vectors. For example, like U1 to UD, they are all in the RP as well. So this could be just some random vectors, right? Some like you pre-specify some and vectors. Then my feature phi x will just being sum of h1 of x to the h of d of x right here. So there are a bunch of choices of hj of x right here. So where this hj of x, it can be multiple ones. The first one, it could just be the inner product of x's with u's, and then you square them. So this could be just x dot uj. So this is an inner product, then square that. Or what you can do is you can take cosine of x dot of uj. Right, so this is also possible choices. Another possible choices could be 1 over 1 plus exponential of x dot uj. Right, so you can see these are all possible choices for those and for those like new features that we can generate for those high dimensional and 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 the features directly. Okay, so and then let's go back to this and cross validation, and I want to show you how to using cross validations um, and to prevent overfittings. Okay, so in this lecture, we're only going to show the most commonly used one. It's called holding out. Okay, so I will tell you and tell the whole story and momentarily. So and then let's just think everything in more generic settings, because I mean this is here we're talking about linear regressions, but this whole strategy actually can be pushed out to any other situations that you can any other models. So so you can think about we're trying to fit and regression models. On this training data set. So we have a training data set like this. And we say we find out the best models under some situations. So we computed these like predicted values. So basically this will be f hat of x of y. So this will be predicted values. So if this predicted values is close to the truth, which is yi, then we know this RSS or MSE or like negative log likelihood will be small. So that means they're close. So I mean, in some senses, training error is low. But unfortunately, we are not interested in whether this is an f hat xi is close to yi or not. This is something just for the training data. So the fundamental things that we are interested in is, so I want to change the color here. So we are interested in if you are giving a new data. So this is some data that never been seen before. A new set of data. We want to know whether this f hat of x0 is actually, I mean, equal to y0 or not. So I don't care whether those training data are well fit or not. I want to see, I mean, if I have a new data that is coming from the same distributions, I want to see whether they can give a good predictions or not. And the key here is these data right here is unseen before. So unseen so validations data set. So the key is not used in training. So during training, we never seen this kind of like, and this data set at all. So the goal here, so basically, and let's set up a goal. The goal here is to choose methods that gives the lowest test MSE. Rather than the lowest training MSE. So if we have a very large number of the test data, so I mean the goal that means is we actually want to minimize the expectation of the, and we want to minimize the whole expectation of, we want to make sure this the ground truth of y0 subtract the predicted and a test data set, and this thing should be minimized. And these data are all testing data set, not the training data set. So the method right here is we're trying to and mention here, as I said, it's called holding out. So what is holding out here? So I need to define something called like a generic form of error. So it's called ERM. Let's see. So ERM, what is the ERM means? I think it's oh yes, it's called empirical risk minimization. So this actually is a very generic formulation about error. So this is called R D. So D is actually the dimension of all the complexities of my models. Okay, so you can think about this D is the number of dimensions of my files right here. Right, so the number of dimensions that we choose of the degrees of the freedom of the polynomials. So this is theta is the parameter, and we have the data, which is D. So this is 1 divided by D. An absolute value of a set is actually the cardinality of the set. Sum of all possible situation for the D, then L of Y, of F D of X of theta here. So right here is the ground truth. Here is the predictions. And this is some errors that we can predefine right here. So if the ground truth and prediction are close, the error is small. If they are different, it will be big. So the first approach is we're going to divide the whole data into two disjoint and a set. So this is, say, my D here. So I'm going to split this into two parts. The first part is the D train. The second part is D test. So the way that we split out, we ensure the training set and testing set is disjoint. So that means my D is actually D train union of the D test. And also I want to emphasize the D train and an intercept with the D test is actually precisely an empty set. So usually this will be 80%. This will be 20%. Okay. So what we do is, so this is the first, on the splitting, the whole idea is we're going to fit the model on D train and evaluate performance on D test. Okay. So, and what does that actually means? We are going to compute some, on the first part, so this I will call it A. So first part is the fit the models on a D train. So that means we're going to find the optimal theta in the dimension of D, that we fix a D. We're just using the D train. This will be argument of theta. And that will be RD theta D train. Okay, so basically we are using the training data set to find out and to find out optimal theta to minimize this ERM. So this will be my optimal parameter for fixed of D. Then you're going to calculate the validation error. So the validation error is actually, we're plugging back this RD with optimal theta had trained on the training data set, but evaluate on this testing data set. Okay, so this is, I'm actually the testing error. So this is testing error or validation error. Okay, so this is the second step. The third step is, so, and through here, we fix the D. Right? So then we are going to vary the D. So what we do is we choose the D such that it gives best validation performances. So here is the key is we choose the D, it doesn't based on the training error. Instead of we choose the D that based on the testing error. So that means we are going to fit the models for each value of D. And then we are going to pick the optimal D star such that to minimize the and validation or testing error. So that means D star is actually the argument of D of RD value. So you can see this is actually how we choose the optimal D star here. The number 4 is optional. That is after picking the optimal value, optimal parameter we can refit the models to the entire data set. So that means this will be theta d hat of the whole d. So we combine this d back. Okay. Then since we have set out the d here and the d star here, so we're going to refit that to find out if we fix the d equal to d star, what will be an optimal theta hat here. So this, to ensure, since we have more data here, my theta hat will be more accurate in these cases. Okay, so this is how we actually do that. So this is the strategy called holdout. There are other strategy for for example, the k-fold cross-validation. We're going to talk about this later on. Okay, but for now, let's just stick with the holdout. All right, so I have talked about this strategy. Let me just demonstrate that with the programming here. So that's the same notebook we have seen before. Okay, so here is the difference here. Here we're using this train test split from scikit-learn. It's just for the convenience here. You can also write your own if you need it, but for this whole courses, you could use this function right here. And we're going to try different Ds, D ranging from 1 to 19, I believe. So this is a lot of choices here. And we'll actually need to hold out this out. For example, this is the number of training data here. So, and we are going to stacking out ones and as well, just to make sure we need to include this like intercepted terms. So that means we are going to, for each of D, we need to add this training and reshape this training. So basically they start with column ones, then we need to add this x0 power of D. So this is what, and we're thinking to using this kind of polynomial features right here. And same thing, you have to do it for the testing data set. Then for each D, we know the training and the testing, the column will be increased by 1, right? So as the D increases. So then what we do is we're going to store and find out this W and store this and the W as well. But the most important part is we are going to find out this and the predicted Y for the training and the testing. So then we are going to calculate an ISS for the training and ISS for the testings. Okay, so you can see right here, it's quite interesting. You can see this training error is always, RSS is always decreasing asymptotically. However, the testings will start to drop from D equal to 1 to 2, and then gradually start to increases here. So what does that mean is this testing error or validation error actually demonstrate this U shape. We have shown that in the first week of the lectures. And from here, we see the sweet spot of this D right here, which should be 2, as we expected. All right, so we can find out, and also we can find out the norm of this W. You can see this start to increase a lot when my D is really large. You can see right here, this and the W, which is my norm of my coefficient, is super large. If we actually look the cases that is believe D equal to 19, you can see this is the coefficient. And you can see it actually varies a lot. It could be as large as, I believe, 200, and it could be as small as nearly close to 0. So you can see this, and actually has a like very large range of and of the parameter. And you can see here we have a minus 200, and here we have a plus 200. You can see they are like oscillating here. So that just gives you some idea. It might have a big issues on the on overfittings. So there are two signs that you can see for the overfittings. Is you can see this oscillating coefficients, or you can see the norm of my weight is super large. This is also an indication that we have overfitting issues. And of course, you can see that, always see that from the validation error here. And you can see validation error right here is significantly larger when D equal to 2. Okay, we can, I'm actually going to plot them out to see. This is, I mean, for the second, this is basically and D equal to 1 cases. This is a straight line. And this is, sorry, the first line right here. I think I'm might be make mistake here. This should be data here. I think it should be like that. The first, which is D equal to 1. Oh, PLT is not. Why? PLT is not defined. Should define it right here. PLT. What is PLT? PLT is not defined. Wait. Okay, so let's rerun this thing. I think. So this is actually to try the 3 possible cases, which is D equal to 1, D equal to 2, and D equal to 19. And we know when D equal to 1, which is a straight line, I mean it's an underfitting. So this is basic says the D equal to 1 is underfitting, and the D equal to 19 is overfittings. I don't know why this takes so long. Didn't take that long. Okay, right here. So you can see right here, for a straight line, you can see it doesn't fit very well. I mean, so this is the with the and a quadratic, and that you can see it. I mean actually, and it fits very well. And for 19th, it has like a lot of like and wiggling here. So I mean it's unnecessary. So that's why it creates overfitting issues. Okay, so right here, so this is another test. That means I'm going to and create and more points right here. And it's like basically I'm exact the setting, but the difference is I'm going to run 20 times, right? And for each of that, and we're going to run from 1 to 14 for like different Ds. So everything is the same, but difference is we're going to run this and a curve right here, not just for 1 time, but we're going to run this for 20 times. I mean, if we run this 20 times, you can see this training error is always decreasing, right? So it's always monotonically and decreasing from 1 to 15. But the difference is here is for this RSS for the testing error. You can see this has a huge variations right here. And for some like times this values could be shoot up to be very high right here. So you can see for small d, and we always has a high biases and a relatively low variances here because they are all very small. The variances of error is very small right here. If we have a very large d right here, the bias will be small right here. You can see this training error is and it's monotonically decreasing here. So you can see the value and right here is and the bias is very small. But the problem is it has a huge and the variances here. So the variances of this errors changes so dramatically from ranging from like close to 0 to nearly 2000 when the d is really large. So this to indicate the following things is this validation and this validation error. I mean, when d is large, could be very highly variable and depends on the position and precisely which observation that to include on the training set and which observation being used on testing set. And the way how you split the data actually can make contributions on this and the validation errors. And you can see in our approach, only a very subset of the observations that are included in the training set rather than in the testing set are used to fit the models. So, and usually this kind of the method will tend to perform worse if we train on the fewer observations. That means, and all these testing error will tend to overestimate the testing errors for the models on the entire data set. So that means if we like using and more data set, these testing errors will be more reliable. But in any cases, you can see there is some trend here and a very interesting trend. If we run this 10 times, it gives you a very interesting phenomena by looking at this RSS for the testing data set. And in particular in these two regime for the smaller d and versus and the large d. So this is like overfitting and underfittings in the situations. Okay, at last I want to talk a little bit on the situation that is called robust linear regression here. We are not going to talk about this in detail, but this is just something that you keep in mind. For example, right here, we have some outlier right here. If we and our data has some outlier, and this is the solution for the least square because and the least square will like favor those like be favored by those outlier status. So that's why I mean if you believe your data has some outlier, what you can do is you can using one norm instead of two norms, because if we're using one norm, these errors like outliers doesn't have a very large contributions to it. Then we can and sort of like avoid those outliers. There are other tricks that to change those up, and there are okay. But the issue is if we using one norm, and the whole thing might not be differentiable. So that's why I mean this whole thing, right? An absolute value of epsilon is not differentiable at epsilon equal to 0. But we have some like subderivatives, and we're going to talk about that in the last. So we can and use some like coordinate and gradient descent algorithm. This is something that we have been used before. But as another choice is we can using some like smooth surrogate for this whole thing. That means it's something called a smooth relaxations of the one norm. So the way we do is and if my epsilon value is bigger than delta, it will be just be close to and the same as the an absolute value of epsilon. However, if it is smaller than this region right here, it will be replaced by a quadratic function, which is epsilon squared over 2 delta. So this is something called Huber loss. So this is something called smooth relaxation of the one norm of my error here. So I mean, if we choose this kind of an surrogate or smooth relaxation, this can be minimized using standard gradient descent. You can use a bunch of like numerical and optimization techniques to actually help to find the local minimums for these problems. Okay, so that's all for first part.